today what we're going to do is we're going to talk about polygons. It's pretty quick and painless. Your homework is pretty short as well. You should have time to work on Tinkercad if you need time to do that still, if you need help with that. I'll get you caught up on that in a little bit. Then tomorrow we're going to be reviewing sections 1, 2, 3, and 4. So what we did on Friday with all the basic terminology, yesterday was angles, today is polygons. Okay, that'll all go into our review tomorrow. We have a quiz on Thursday. Okay, that's the plan for the rest of the week here. Is that good? All right. It'll be okay. It'll be all right. Regardless of what happens, it'll be okay.
If I cry, just don't look at me. Just like look over there. I don't know.
All right. So the first thing we need to do is we need to define what is a polygon. So poly means many. It's really just a many-sided figure. Okay. Formal definition of polygon. It's a closed figure in a plane. Okay. So we're still talking about that plane. Formed by connecting line segments endpoint to endpoint with each segment intersecting exactly two others. Okay. So the endpoint to endpoint to create a closed figure. So on the left here are all examples. On the right, those are non-examples. Okay. So let's look at the non-examples. So first of all, this ovalish shape here, that oval there, is not a geometric figure to begin with. The oval is not really an identified shape by the geometric community. We deal more with ellipses. But the oval is not made out of segments, so it can't be a polygon. Okay. This figure here, its endpoints are not connected to any other endpoints. It's just a segment. This figure here, the two endpoints are not connected. If I were to ignore that part and that part, the triangle itself would just be a polygon. But because it has those segments that are hanging out there, the endpoint's not connected to an endpoint. And then here, we have the problem that the segments are intersecting again, but they should be intersecting at the endpoints. Now, the triangle on top all by itself would be a polygon. The triangle on the bottom all by itself would be a polygon. But if you look at the entire figure, all of it together would not be considered a polygon. Is that okay? All right. Next thing you need to know are the common names. So for standardized testing, not just air tests, but like ACT, SAT, even really into college, you really need to know the specific names of polygons 3 through 12, 3 sides through 12 sides. Okay, you should know them by name. So most of these you're going to recognize. Like a 3-sided polygon is called triangle. A 4-sided quadrilateral. Some that are not always recognized, 7 is heptagon, 9 is nonagon, 11 is an endecagon, and 12 is dodecagon. Okay, those 4 are kind of the wonky ones that people don't always know. The others people usually know. After 12, we start referring to them as n-gons. So n means any number. So if it has 15 sides, we would call it a 15-gon. If it had 32 sides, we'd call it a 32-gon. Anything 13 and up, you can refer to as that number gon. Okay, it is not okay to say draw an 8-gon. Okay, you have to say draw an octagon. Questions on that? There is a name out there for a 15-gon. There is a specific name out there for 32-gon. Only 2 people know it. Google and the person who invented it. Okay, the person who named it, because nobody remembers all those. You can Google it if you want. All right, next thing we're going to talk about is concave versus convex polygons. Okay, concave versus convex polygons. So there's 2 different types. So first of all, before we can figure out how they're different, we need to learn about this thing called a diagonal. So if I ask you on your page of notes is a rectangle, right? If I ask you to draw a diagonal, draw your finger where you would draw a diagonal. Opposite corner to opposite corner, right? Is there more than one? There's 2 of them, right? Okay, so that's nothing new for us. This would be a diagonal, that would be a diagonal, right? By definition, a diagonal connects non-consecutive vertices. Okay, consecutive means in a row. Okay, so if I'm starting from this vertex here, this vertex is next to it, and if I were to draw a segment there, that's just a side. So I'm connecting non-consecutive vertices. So this vertex here is non-consecutive, meaning not next to. Does that make sense? Okay, so we're used to doing it with quadrilaterals, really. So there are two diagonals in all quadrilaterals. Let's think about a pentagon. Let's think about a pentagon. I'm going to start right here at this vertex. Okay, if I were to draw in a diagonal, it has to connect to a non-consecutive vertex. So this vertex here, that is consecutive. It's right next to it. But here's a diagonal, and here's a diagonal. This one is next to it. So from that one vertex, I can draw two diagonals. Okay, so let's go to the next vertex. I should have two diagonals coming out of this vertex as well. Okay, so this one down here would be consecutive. Here's a diagonal, here's a diagonal. Go to this vertex next. I should have two diagonals coming out of that vertex. I already have one drawn, so I don't need to draw it again. Then I would have this diagonal as well. This vertex should have two diagonals coming out of it. I already have them drawn, right? So how many diagonals are in a pentagon? Should have 5. You work on the hexagon. See if you can figure out how many diagonals are going to be in our hexagon. What do you think? Any guesses? Should be 9. I guess 4 would be the same number. Don't double count. So if you've drawn it once, you don't need to draw it again. All right, so there should be 9. So let's look at it. All right, so starting from this top vertex, this would be a side. So this would be a diagonal, and a diagonal. So we should have 3 coming out of each one, right? Okay, there's 3. From this vertex, we've got 4, 5, and 6. From this vertex, I already have this one drawn in. So there's 7 and 8. From this vertex, I have 2 of them drawn in. So here's number 9. This one has all 3. This one has all 3. So there are 9 diagonals in every hexagon. You ready to do it for a hexagon? How about a nonagon? That'll get mighty ugly really quick, right? Okay, so not very often do you actually have to draw these in. But the reason we teach you about diagonals is because, notice, barring my sloppy drawing and my big points here, all of these diagonals are contained within the shape itself, right? It's contained within those polygons. If you have a concave polygon, you will have at least one diagonal that is outside of your figure. Okay, so it's concave if the diagonal, oh wait, that's not. outside of the figure. Okay, so even if you have one diagonal that falls outside the figure, it is considered a concave polygon. If all your diagonals are inside the figure, it's called convex. I don't have to draw them all in to see that I'm going to have one outside. Right? Like here, I can see I'd have one outside. I can see I'd have one outside. Now, concave and convex, you probably have heard of in science class, right? They usually talk about that with lenses. Okay, so do you remember when they talk about concave, it makes a cave? Okay, same thing happens here. If you can rotate your polygon to make a cave so you can stand in it, stay dry in the rain, it's concave. If you can see it then. In geometry, and this is not just this class, this is universally accepted. We assume that polygons are convex unless it specifically says it's a concave. Okay, so if it just says a polygon, a hexagon, whatever, it's going to mean convex unless it says a concave, whatever. Does that make sense? All right. On Friday, we talked about congruent segments. Yesterday, we talked about congruent angles. Well, we also have congruent polygons. Okay? Congruent polygons have corresponding sides and angles that are congruent. Corresponding means in the same position, basically. So, for instance, look at my tick marks. One tick mark for this side, one tick mark for this side. AM has to be congruent to IT. Those are called corresponding sides. Okay? This side, MP has 2 tick marks, TE has 2 tick marks. They are called corresponding sides because they match up. Same thing with angles. Angle A has 2 tick marks, angle I has 2 tick marks. They're considered corresponding angles because they both have 2 tick marks. Okay, that's what the word corresponding means. Now, notice that these two figures have to be exactly the same. I can turn one on its side, but it still has parts that match up. They don't have to be oriented the same way, but they do have to have all, in this case, 8 parts that match up, 4 angles and 4 sides. So we were writing congruency statements for congruent segments and congruent angles. This is a congruency statement for congruent polygons. So it names all the vertices, and it names them kind of in a specific order. So I didn't call it campsite just to be funny. So what happens is you start with one point, and you have to work your way around the figure in a circle. It doesn't matter, first of all, which one you start at, and it doesn't matter whether you go clockwise or counterclockwise, as long as you're consistent. Okay, so if I go CA, M has to continue to go around the figure in a circle. So that's why I went CAMP. I cannot zigzag back and forth. Okay, we're going to practice that in a minute. Same thing here, right? SI, then T had to continue around the circle, in a circle, I should say, E, and then back to S. All right, so the powerful thing about these congruency statements is I can tell a lot just from looking at that congruency statement. Those letters are put in a very specific order. Again, not just to make words, but this tells me that there are 4 vertices, so I know it has to be a quadrilateral of some sort. Letter C is listed first here, and letter S is listed first there. So that's an angle and an angle. I know that C has to be congruent to S. So angle C in my picture has to be congruent to angle S. If I look at the second angle, A and I know those have to be corresponding. I know they have to be congruent. M is going to match up with T. P is going to match up with E. So the angles have to be listed in order so that they match up. If I wanted, I could rewrite this. I could list A first. If I listed A first, what would I have to list first for this guy? The I. And then if I listed M, then I would have to do T. Okay, so as long, T would be over here. But as long as you put them in the right order and match up the pieces, you have some flexibility. You can also tell segments though. So for instance, segment CA matches up with SI, right? How about segment MT? That's the third and the fourth point, so I'd have to go with the third and the fourth over here. Okay, so all of that is very specifically laid out. Any questions on that? All right, I'm going to have you do a practice here of drawing. So yesterday, remember we did number 20, and I talked to you about read the whole thing first, and then go back to the beginning, read, and as soon as you can draw something, stop and draw it. And then read, stop and draw. Read, stop and draw. Stop and draw, right? Okay, so that's what I want you to do. It says draw hexagon ESKIMO, where ES is congruent to IM, and EM is congruent to SI. Okay, so take a minute to think about it on your own, then talk about it as a table group, and then we'll talk about it together.
She makes it words on purpose. Are you doing this to us on purpose? Like, they have to put the words. Yeah.
Makes it a little more interesting. It makes it easier for me to check it too. Because if you're not spelling the word right,
I definitely flavors. Don't like I'm not, don't like
That is the coolest thing I've ever seen. But it was not the coolest thing I've ever seen in my entire life.
the paper thing,
Yeah.
got that at $6 for $1. Right?
I don't know if it was right. I think I did it right, but I don't know. But it might be. Oh.
Start comparing with your partner, please.
I'm trying out. So there's first, second, third, second. First doubles and second doubles. First,
Now,
they've got a similar thing going like in this text. She always has everything down. Fiance's name is Chris. You were towards that? She told me she was gonna throw me into the river.
Yeah.
All right, so let's start talking about this. Let's start talking about this. So remember we said read it all first and then start at the beginning. So it says draw a hexagon. I can draw a hexagon. How many sides does a hexagon have? 6 sides. All right, so here's my hexagon. Now it named it ESKIMO. So it doesn't matter where I start with my E, but when I start naming it, I have to go in a circle all the way around. Okay, or I could have gone E-S-K-I-N-O. It doesn't matter if you go clockwise or counterclockwise. Okay, next thing says where ES is congruent to IN. ES is congruent to IN. If you have a terrible drawing, as long as you have those tick marks, you're good. You don't have to redraw it and try it over and over and over again. Then it says EM is congruent to SI. I don't have a segment EM, but I can just draw it in. Because E and M are endpoints, right? I can draw them in, so EM and SI have to be congruent. How many tick marks do I need to have on that one? 2. What if I said that, what if I wrote this, added it in? What does this mean? Parallel. What if SK is parallel to OM? How do I show lines are parallel? The arrows. So I would need to draw an arrow on SK and on OM. If you want to add that in, I'm just throwing it in. Is that okay? Yes. All right, so this is where that people get all freaked out because you don't have those segments, but that's why it's super important to draw as soon as you can. Stop and draw bit by bit by bit. Okay, you're gonna have more of those for homework tonight as far as sketching things out. All right, last 3 terms. The last 3 terms, we have different types of polygons. In this example, I drew in pentagons, but this really works for any polygon. Okay, equilateral polygons. Lateral means side. This means equal sides. So all sides of the polygon are congruent. Equiangular. Equal. Angular sounds like angle, right? So that means all the angles are congruent. So that is equiangular. Now we have something called regular polygons. Regular polygons are both equilateral and equiangular. Okay, they have to be both equilateral, both equilateral and equiangular. Okay, so all sides are congruent and all angles are congruent. I'll get out of the way. All sides are congruent and all angles are congruent. Now, I'm never going to ask, I probably would never ask you to draw a polygon that's equilateral but not equiangular, equiangular not equilateral, but it's kind of hard to envision. So I gave you an example here. So these octagons, the first one is equiangular. All the angles are the same, but really they just seem like the sides of the octagon just kind of pulled and stretched them. So it created opposite sides here that are longer, but they maintain their angles. This egg-looking one here next is all equilateral. All the sides are congruent, but they didn't hold the angles true. Okay, then this is your regular octagon. Regular polygons are kind of the pretty ones. So when you were in kindergarten, first grade, preschool, and started doing shape recognition, okay, and they gave you a pentagon, they didn't give you a pentagon that looked like this to try to trick you, right? They gave you the nice pretty one that looks like the pentagon in Washington, D.C., right? They gave you the one that has all equal sides, all equal angles. So they're the ones that are like perfect looking. Okay, that's another way to kind of think about it. That makes sense? All right, so for homework, you have some problems out of your book, some drawings with them, labeling parts, that sort of thing. It's not very long. It shouldn't take you very long. You're welcome to work on that. You're welcome to work on Tinkercad. If you have both of those done, you can work on another assignment or anything else, whatever you need to do. Good?
No, I haven't been to like